Hello everyone and welcome. In this video I will show you how to build a qubit. Just like we have many ways of realizing a classical bit in a classical computer, solid-state drives, hard drives, or old-fashioned CDs, in the same way there are several platforms to realize a qubit. For our purpose I will sort them into two categories: non-solid-state qubit platforms and solid-state qubit platforms. In the non-solid-state qubit implementations, two major platforms have emerged. The first one encodes the qubit into photons. One way to do so uses the polarization of the photon. The polarization is the orientation of the electric field, which can be vertical or horizontal. Mapping this to the Bloch sphere, vertical and horizontal are the south and north pole. The plus and minus states become diagonal and anti-diagonal polarizations. The plus I and minus I states become rotating polarizations. Plus I rotates clockwise and minus I rotates anti-clockwise. In this way, we can differentiate the two polarizations and measure the state of the photon. These approaches can be used to not only build photonic quantum computers, but also to connect quantum computers and send qubits between them. Thus, photons also play a vital role in quantum key distribution. The second platform in the non-solid state category is trapped ions. As the name suggests, this platform is made of electrically charged particles in a trapped alternating electric field. The electric field looks like a saddle, with the ion being the small gray ball in the center. This is done at a high vacuum such that the ions are well isolated from any environment and can be cooled. Once the kinetic energy of the ions is low enough, so that they are in a ground state, we can deliberately excite them using lasers and read out this excitement with a camera. The qubit state 0 and 1 are the ground state and the excited state of the ion. State-of-the-art traps can store more ions than you can see in the image, where every colored blob is one excited ion. Therefore, they are a promising candidate for larger systems. When it comes to solid-state platform, there's a large variety of implementation. For this video, I will focus on three of them. The first one is, thanks to Google and IBM, probably the most well-known platform and consists of superconducting qubits. The most common implementation is the so-called transmon qubit. The term transmon is actually an abbreviation for transmission line shunted plasma oscillation qubit. In simpler terms, the physical system is an anharmonic oscillator. As you might know, a harmonic oscillator has energy levels that are equidistant to each other with a spacing h times f, the resonance frequency f, and the Planck constant h. In the anharmonic case, the higher energy levels are shifted with respect to each other. The higher the energy level, the closer together they are in energy. This allows us to selectively address specific transitions in the oscillator. Usually, the first transition, F01, is used to encode a qubit. Gates and measurements are performed using microwaves in nearby superconducting resonators. So far, this approach has scaled very well, and processors with over 50 qubits have been demonstrated. The technology can be regarded as the workhorse of quantum computing technology. Another solid-state approach relies on nitrogen vacancy centers, or in short, NV centers in diamond. To ease the understanding of exactly such a nitrogen vacancy center, let's take a look at this crystal. If all the black atoms here were carbon atoms, we would have a regular diamond that you could buy at your local jewelry. To get an NV center, we first remove one carbon atom and then replace an adjacent one with a nitrogen atom. The nitrogen atom is green in this animation and offers one additional electron, which is depicted in red. Thanks to microwave signals, we can transform the spin of the extra electron provided by the nitrogen atom into a qubit. But we can not only use the extra electron as a qubit, but also the nitrogen atom itself. Then we use light to encode the qubit. Since these NV centers couple well to light, they are a prime candidate as local nodes for quantum communication using photons to transmit the information. The last platform I want to introduce consists of semiconductor quantum dots. The latter can confine a few or just single electrons, enabling the use of their spin as quantum degree of freedom. A quantum dot, or single electron transistor, is a structure very similar to the classical field effect transistor that is the fundamental block of every digital logic circuit. The difference with respect to a regular MOSFET is that a quantum dot creates an island on which it can isolate electrons. Confining electrons in a quantum dot requires operation at temperatures close to absolute zero in order to suppress charge fluctuations into and out of the dot. Now, let me show you how to build such a dot. We start with a bare wafer, a disk like a CD made from silicon. Every wafer has enough space for many quantum processor chips. Now, we could already work on this wafer as it is, but for reasons I'll get into later, we process it before we make a quantum dot on it. The first thing we do is we grow multiple layers on it. Why do we do that? We prefer to work in a silicon quantum well, and we want this quantum well to be strained. This means the silicon atoms in the quantum well are further apart than they want to be. This strain then helps to define our quantum dot in the z-axis and improve certain electric properties. To create this strain, we mix both in beneath the bottom and the top layer of the quantum well about 30% germanium. The germanium increases the lattice constant and thus strains the quantum well. Then we implement phosphor atoms into some region of the heterostructure. In those regions, we can form electric contacts to the quantum well and inject electrons to load and unload the quantum dot. The following oxide electrically isolates the implanted region. Wait, didn't we say we need to contact those implantation regions? That's right, but now with the oxide on top, we can't do that anymore. So we need to remove the oxide in some places. That then can contact the implantation regions. And now the implantation regions are isolated except for those regions under the metal contacts. These type of contacts are also called ohmic contacts. This heterostructure with ohmic contacts defines the quantum dot in the z-axis and electrically isolates all subsequent metallic layers. Exception to this isolation are, of course, the ohmic contacts, which are deliberately in contact with the quantum well. Now that we have this structure, we can look how to define the quantum dot in the x and y directions. For the definition of the quantum dot in the xy plane, we can create electrostatic potentials with metallic gates. These gates are created in a liftoff procedure. Let me show you how. We start by coating our processed wafer, the blue and purple cube, with some sensitive polymer, the red layer. We illuminate the red layer using light or high energy electrons with the pattern of the gates that we need. This illumination steps allows us to dissolve or develop these parts more easily. After that, we evaporate a thin metal layer on both the resist and the substrate. Afterwards, we then dissolve the remaining polymer. By doing so, we remove or lift off all metal that was on top of the resist. This procedure only leaves the metal where we illuminate the polymer. Now we have our gates. If we need a second layer of gates, we again need some oxide to electrically isolate the first layer. After the oxide is deposited, we can go back to the first step and start over. Even though these steps can in principle be repeated many times, in practice we seldom use more than a few layers. The final step, after all layers are deposited, is to cut the wafer and separate each quantum processor chip. With an appropriate gate pattern, which could look like this one, and the corresponding schematic cross-section, we now have a fully working quantum dot with a discrete spectrum that we can use to make qubits.